Welcome to this short presentation of the hot stage microscope Misura HSM. This instrument was first developed by Expert System Solutions in the year 1990. In the following years, it was continuously updated and developed, and now it is currently used by many companies which work in several industrial fields like glass, ceramic, enamel, steel, power generation and waste management. The hot stage microscope is the ideal instrument to study phenomena like softening, melting, swelling, burning at high temperature on materials like glass, ceramic, metals, casting, lubricants, and flying ashes from the combustion of fossil fuels or from the waste incineration. Thanks to the restless research effort, Expert System Solutions has now implemented the measurement of the surface tension using the method of the analysis of the profile of a sessile drop. The hot stage microscope Misura HSM is now the only instrument available on the market which can measure the surface tension on molten materials up to 1600 degrees centigrade. In order to carry out the softening and melting tests, the hot stage microscope Misura HSM uses a cylindrical specimen with 2 mm of diameter and 3 mm of height. This specimen is prepared with a small manual press which is supplied with the instrument. It is also possible to follow the behavior of specimen with an irregular shape or analyze 2 specimens at a time. The specimen is positioned on a sample holder rod and it is inserted into a tubular kiln. Misura HSM is available in several versions, with a heating rate up to 80 degrees centigrade per minute and up to a maximum temperature of 1600 degrees centigrade. The image of the sample is captured by a digital camera equipped with a microscope with a very long focal length. The image is transferred to the computer, and since the picture includes the sample holding plate, the system automatically corrects for displacement of the sample holder. For this reason, it is not necessary to run a calibration curve. This is an example of analysis of the softening of a ceramic frit. The heating rate is 50 degrees per minute. The image acquisition starts from the temperature set by the user, and in this case it is 600 degrees centigrade. The size and the shape of the specimen are automatically analyzed. Let's follow the analysis when the material is already above 1000 degrees. The shape of the sample is changing because the material is becoming liquid, and the surface tension is trying to reduce the surface of the sample to the minimum. At 1100 degrees, the material is completely liquid and the shape of the sample becomes spherical. In order to get the sphere shape, the sample must be very small. In this way, the hydrostatic pressure, which would flatten the drop of liquid, is negligible compared to the surface tension. In order to carry out surface tension measurement, the sample must be much bigger, and so the sessile drop will be more flat. The heating of the sample may go on up to the complete flattening of the sample, which corresponds to the melting. The control software will automatically stop the test when the sample reaches the flattening. This function can be configured by the user, and it is very useful for the test of unknown material. Some material may react with the sample holder and damage the thermocouple. The images taken during the test can be seen as a movie and exported in AVI format. Looking at the movie at higher speed, we can enhance the transformation of the sample. In the initial part of the test, the material undergoes a simple thermal expansion. Then the sintering process starts and the shape is maintained while the dimension is getting smaller. At a certain temperature, the liquid phases are emerging on the surface, provoking the softening of the sample. From this point on, the surface tension is taking control of the shape, which is continuously changing to sphere, half sphere, and finally complete flattening. The data gathered during the test can be seen as a plot. This is an example of the softening plot of a glaze. The lilac line on the plot are the temperatures of sintering, softening sphere, half sphere, and melting, which are identified automatically. It is also possible to extrapolate the value of the viscosity of the molten glass, using the information from the hot stage microscope and from the optical dilatometer Misura HT or LT. This calculation uses the VFT equation with known values of viscosity given to the temperature of a glass transition, softening, and half sphere. This is an example of animation of two samples of different minerals. The images are synchronized by the temperature. In this case, we can see a comparison between the incoherent melting of sodium feldspar, which become progressively liquid forming a glassy phase, and the melting of a diopside, which is becoming suddenly liquid when it reaches the melting temperature. Another very interesting comparison is between the swelling behavior of different flying ashes. We can clearly see the swelling after the softening and the incoherent melting, which give rise to high viscosity liquid state. The lubricants for continuous casting are becoming a very important technological auxiliary in the continuous casting of steel, because they enable higher casting speed. The two materials shown in this example are spray dry powder used as lubricants for the steel casting. The images can be printed out as a complete sequence or as a selection of the characteristic shapes, which are automatically identified. The latest development on the hot stage microscope makes it possible to measure the surface tension using the method of the analysis of the profile of a sessile drop. This is the image of a molten drop of soda lime glass on a platinum foil. The calculation of the surface tension at 1100 degrees centigrade gave the value of 346 by 10⁻³ Newton per meter, which is in a good agreement with the bibliography. This is a sessile drop of molten solder over an alumina plate at 200 degrees C. The measured value is 482 by 10⁻³ Newton by meter. The calculation of the surface tension is made possible thanks to the development of a new mathematical algorithm. This function is based on the assumption that the curvature of the surface of a sessile drop is given by the differential pressure between the internal and the external surface, given by the surface tension. Each point of the surface of the drop can be described by two curvature radii. The two mathematicians, Young and Laplace, wrote the equation which describes the curvature of a sessile drop as a function of the surface tension almost 200 years ago, but this function has no known analytical solution. The solution for this equation can be found using an algorithm for numerical integration, which solves the equation by iteration until the calculated drop profile fits with the image profile. The curvature of the drop profile is also dependent on the density of the molten material. Since it is nearly impossible to get a direct measurement of the density of the molten glass, we use an extrapolation method. The density of the glass at temperatures higher than the transition temperature is extrapolated extending the thermal expansion curve obtained with the optical dilatometer Misura LT. This instrument is carrying out the measurement with no contact and it is not deforming the sample. The part of the curve above the transition temperature, Tg, and before the softening can be several hundred degrees wide. This is the main window for the surface tension measurements. The shown example is the measurement of the surface tension on a drop of distilled water over a Teflon plate at room temperature. The measured surface tension is 70.3 by 10⁻³ Newton per meter, and it is in perfect agreement with the values obtained on water with all the other methods. Thank you for the attention in following this presentation of the features of the hot stage microscope Misura HSM.